So in this tutorial, what I would really like to go through is, this is a very similar tutorial that I gave in the Indaba, in the 2018 Indaba workshop in South Africa, but I find it very relevant for the current context in terms of understanding what is probability, because this week you need to really kind of, when you read the paper, when you read different blogs, you need to have a certain kind of framework in your head, how you are going to interpret, how you're going to understand, how you're going to see probability and the probability distributions and related items. Okay, so I'm going to go through just really what is inference in science. This is the whole probability thing. The whole thing we do with data science is inference, because we want to get, like, so that terminology is like, we want to get something unknown and we want to infer about it. And that's like, and then we assume there is some logical process going on and we want to get some insight out of it. And that's the whole thing. So when we say inference, is really just, that's what almost everything in science, every science is doing that. And so I'm going to start what kind of inference there are. So there are different types of inferences, but there are mainly two. But I'm going to just give that one. And then I'm going to give you also just like, what is probability theory? In particular, what is like probability and how do we assign probability? Because those are fundamentals. Like, it's like, if you want to start to mathematics, the first thing you have to know is what is a number and how do you assign a number. That's so, of course, by now, it's complicated. It's like, even that assignment of numbers, from the beginning, we have been told to start counting 1, 2, 3, and then we have been kind of conditioned to know what is one. It's either one bread, one chicken, one box, one table, one chair. So it's kind of, we change this, but it's a unit. Of course, if we don't get philosophical, great. It's like a unit, whatever it is. It's one house. If you don't want to, to refer to the table, just consider it one house. If you don't want to refer to that, call it just one country, which contains everything else. Okay, that's kind of object-oriented, right? So it's like, instead of really just doing, we kind of objectify something. So if we don't want to refer planets, then we say one solar system. No, if we don't want to do that, one galaxy. All right, it's a number, but it has a very clear thing, but its interpretation is really different. While the system, the syntax part of it, which is just one, is always the same, and it applies. And it's up to, if someone knows galaxy, it's easy to understand galaxy. But if someone, for example, doesn't know about topology, and if I say, like, in that topology, one in that topology, you probably start like, okay, I don't understand that. So probability is the same. It's mathematics, but interpretations are different. That's why we're going to be looking at just how do you assign probability. That's what makes it complicated. And then from that also derives, of course, what is probability. And then there is something that you sometimes need to sample. Almost everything is a sample. All the data that you get is a sample, okay? Because it's kind of sample. You don't get, it's very rarely you get the entire universe, like data. So like, for example, if there are people, you don't really get the whole people usually. You get like a sample of the kind of, like, let's say it's the height of the people, then, the height of people in Senegal, then you kind of like get a sample, because it's very rarely, I mean, sometimes it's possible, you can just, if you make the domain smaller, you can get almost every thing kind of counted, but that's rare. And so usually what you get is a sample. And in reality, in particular, if it's like a process, it's basically almost impossible to get a continuous process. So you get only a sample of that process. And then what you want to do is that then to relate, of course, that where does that come from, so with that sampling. And sampling comes, of course, you have a model and you need also to sample from the model to kind of relate it to the theory. And in this tutorial, I really want you to ask, So I probably won't see you, but just unmute yourself or write in the chat such that Sebastian or whoever there kind of could just then unmute themselves and start asking, okay? Because it has to be kind of interactive. In it, I will also ask you, so I expect you to answer, but it's really a lot more about like this, just coming to the basic. But the basic is the advanced. You know, it's balls. So I expect you to be more like, okay, you know, give it your try in that sense. I'm not going to talk about variational inference. Just forget that. And these are references usually, like the first book, I will try to get a soft copy of it. This is a very good, not for this 3 months that we are going to be, but it is the best book I recommend you in terms of understanding statistics, and I mean more data science oriented statistics, Bayesian methods. So it's data analysis Bayesian tutorial. It's a very nice book. And then the lectures, like some lectures on that one. So then it's kind of, I like it to start with this because it kind of will give you a very just brain teaser, but at the same time kind of tells you, makes you think, okay? So one is that you have 5 red balls and 7 blue balls in a container. And suppose so somebody just went and drew 1 ball, but that person didn't communicate to you the outcome of that. And then they went another time, and then they took another ball, so the second time. So they didn't replace it, so it's called you know, sampling without replacement. And then they just took it, and now another ball they just took. Now the question I'm asking you is not like whatever, but I'm asking you, does the probability of the first draw being red or blue? So you would have to take it in your mind. First, somebody just drew a ball. It could be blue, it could be red, and you should assign kind of probability. You know, what is the probability of being blue? What is the probability of being red? But you didn't need to say it. You just keep it in mind. Second time, another draw, and then the outcome is known. So the person told you what is the second draw. Will the knowledge that you have now on the second draw would change the probability that you assigned in the first one, or would you think like it doesn't matter? So that's the question that I'm just asking everyone. Think and answer, just whatever. So either in the text or unmute.
Hello.
Hey. Yes, go on, Elikura.
Okay, basically, the probability that you pick a red ball depends on the probability that you pick the red ball in the first when you first pick, because it's like a conditional stuff. Because if you pick a ball that is red, there will be less numbers of red balls, and normally if you were just picking without any replacement, you are picking without replacement, then it will depend on the numbers of balls that are in the remaining balls that are inside the community packet or the ball. But if you're picking with replacement, then it won't depend. The probability will still remain the same.
Okay.
Because
So
now, if you pick, like if it was 3 before, and the probability before was, let's say, 3/3. Now, the probability will not be lesser than that because it's not 2. 2 minus 1, and 3 minus 1, which is 2.
So do you think that it will change the probability of
Yes,
the first?
it will change. Yes, the probability
Okay.
will change. Yes.
Right. So, and Emmanuel thinks it doesn't. I want more discussion, more example, clear examples. Who can give clear example that will illustrate that? Go on. Because this is, as I said, it's going to be a very interactive one, because if you don't reflect, you don't get it much. So I want you to just reflect and kind of be easy. Okay, no, each is mutually independent. Probability that we ascribe to the second event is not affected by that knowledge. So Stefani also thinks it doesn't depend because it's mutually independent.
Yeah, but I'd like to ask, after the first selection, was the ball returned or it
No,
was
it's
taken away?
not. It is not. So you didn't return it. So it is called sampling without replacement.
And I think it is dependent.
So you think that you should change your probability calculation if someone tells you afterwards what is the second row, you have to revisit.
Yes, I think so.
Great. Okay. The probability will change. The Tome as well. Anyone can give example that could illustrate better. That kind of makes everyone feel, just simple. Make it simple, but make it illustrative.
Hello, can I talk?
Yeah, just go on.
Okay, just to make it more simpler, I think this is we are trying to pick ball. Like let's say we have three red balls now in a ball. The probability that you pick one red ball is 1/3 if you're having three. Then if you're not replacing now, that means if you are left with two red balls in the bowl, now the probability of not picking a red ball is now 1/2 because you have two total numbers of outcomes, and the only possible outcome is one because you're picking one out of it.
Mhm.
I think that explains it because you are not replacing it back. Before, when you the first one before you picked, it was just 1/3. The probability of
Yeah.
picking
So
one
the
red ball is
question
one
the
over three. But
question just
the
to
second,
make it clear, the question is that would your assignment of the first probability, does it change or not? So afterwards you learned you
sorry,
took
can you come again?
so you took one red ball. No, you didn't know what you took. Somebody just
Yes.
took a draw in the first one. They don't tell you, and you had a guess, right? What was the probability? What was the probability? How likely it was red or how likely it was blue. And then a second draw happens, and then that person told you what the second draw was. So they said, oh, it's red, the second draw. And now the question is, would your probability, with assignment of the probability on the first one, will it change based on the information you have after some time, after the second draw has happened? So I think Wamuyu also says she doesn't think it is great. I want somebody to come. Like there should be a way that there should be a very simple example that kind of would help people. So try to think, what is that? Okay, there is Ken also saying no. Olashore she thinks that she think yes. So give one example. I will just let it for 30 seconds and I will get into it. So I think what we got from Lukura is one example, great, but I think there is even a simpler example one can give. Anyone who want to try a much simpler example?
Hello.
Hello, okay, to me.
Let me see if I can give a simpler example.
Go on.
Let's say you are picking. You are picking boys and girls.
Okay.
So, given that you're not replacing them, and then you pick for the first time without saying what you have picked. So the one that you have picked, the probability has reduced for you to picking it to the next time. So if for the second draw, I say what I have picked. Let's say I say that I have picked a girl. So therefore, it means that given that the probability of picking a girl was higher than the probability of picking a boy, so probably the first time I had picked a boy, that's why the probability has gone down, such that I was able to pick a girl.
Okay, so I think I think it's fine, but just changing the thing sometimes makes it simple, but I would still feel there is an easy one, but Rahel thinks it's changed. But great, these are good examples. I mean, go on. Who is that?
I think it changed.
Okay, Rahel, go on.
By giving a simple example. For example, let's say we have two balls. The first red and blue. The first red and blue, we have two balls, red and blue. And if the second was red, then it means the first is blue. But without given the second probability, we have like 0.5 probability of the first being red. But if we know that the second is blue, it means we're fully confident that the first was blue. The first was red.
I think that's what I would say. That I would agree exactly with that kind of very simple example, but I want to know if that is simple for other people to understand. So that I will just repeat it. If you have two balls, one red, one blue, and someone took the first one ball in the beginning, and then you were not told, but then at the second time, they pick and the ball is blue. So what is the probability of the first one of being blue? It's 0, right? Is that so? It's like saying the probability of recovered. That's how you make it complicated, Patrick, in my opinion. but it's like, is it clear? I think this one is very, very like two balls, one red, one blue, you know, and then you get in the first, you are not told, someone took a ball. It could have been red, it could have been blue. At that time, if you were asked, what is no, I'm really, actually it's good, like, you know. Then I mean, it's fine, Patrick. It's nice just to attempt, and I really like that. So one red, one blue, you know, in the beginning, right? You pick up the one ball, and if you were to calculate, it's half, exactly as Rahel said, it's 0.5. And then, but you didn't know, you didn't say it, you just kept it, you know, and then you go on to the next draw, and the next draw, they told you it's blue. Now, if you were asked what is the probability of the first one being blue, you know it must be 0, because the second one is blue, right? And if you were asked what is the probability of being red, then you know it's 1, because exactly that. So this is what I'm saying. Now you have to think, what does that mean? Like, I am changing, like time-wise, they are not connected. Time-wise, like, so that's where the first conclusion, the first thing in your head, in probability, probabilities are connected logically, not causally. So that causal means time-wise. They are not connected by time or anything, but they are actually connected by logic. So it's called a logical connection. Hope that kind of makes it kind of a very first point, how you think about probability. Okay. So there are inferences, exactly as I said, there are two types of reasoning in a human reasoning, and there could be more, but I'm just, from my perspective and my knowledge, there are two. One is deductive. I mean, there are probably, quantum is another one, so it's kind of, let's not talk that one. There's deductive reasoning and inductive reasoning, okay? So what does it mean? In the deductive reasoning is what is all maths about, you know, the mathematics. Mathematics is purely deductive reasoning. Why? It starts with a kind of a clear definition of axioms. So it will specify, by definition, it will specify certain axioms, and then logically you derive some conclusions out of it, outcomes, okay? So that's called a deductive type of reasoning. You specify something. So what does that mean in probability sense? Let's imagine I give you a coin, a fair coin. That statement that I gave you a fair coin, that just is basically the objective. It's an axiom, okay? Because I defined the coin is fair. Now you flip it and you get 7 heads out of 10 tosses. Then you compute probability. That is one type of deductive reasoning. You start from, and usually we call it likelihood. Like, but that's what really is. Just you assume something is right, something is true, and then you derive its consequences. That's a deductive reasoning. The inductive reasoning, which is mostly all science is about, is that you actually don't have one cause, but you have many possible causes. Okay? And then you get certain outcomes. You don't know these outcomes, to which they are related from, how they are related to the possible causes. The possible causes probably are infinite. So, and that is basically a saying, I don't know about, I get 7, there was a coin. You didn't know about anything about the coin. There was a coin, and you had, some experiment was done. 7 heads turn out of 10 tosses. Now, in the inductive reasoning, you're trying to infer about whether the coin is fair or not. So you're actually asking, was the coin fair? And the coin could have been fair, could have not been fair. So that's called the inductive reasoning. That's usually what is really in the probability sense we are talking. Usually we try to infer. So inference is that. We try to infer about the nature, some kind of, question, like in this case, fairness of the coin. In another case, whether, the lambda parameter or the kind of the disease spread rate, whether it is 1 or, 0.5, whether RT, which is kind of like how people are kind of, or the degree of connection between people, is it 7 or 6 or 2 or 3? So that's what really you are trying to infer. Okay, so that's the one. So I don't see anything. So if anyone is texting, just Sebastian, just let me know, okay? Because I'm presenting in my slide. Okay. In this inductive reasoning, if you want to find examples, these are type of examples. Given 5 heads, 15 coins throws, how likely is that the coin is fair? Given the last, yeah.
Hello, Yabi. Yeah, I didn't hear what you said.
No, I'm just saying, if anyone is asking in the text chat,
Yeah.
because
okay.
I'm unable to
raising
see.
that.
Yeah.
Okay. Yeah, Biniam has raised his hand. I don't know if he has.
Okay, yeah, I think he wants to ask probably. So, Biniam?
No, I think I was just posting a question about Bayesian probability, and he was just putting his hand. But I think it's okay. You can just continue. We will test about that.
No,
Okay.
no, I
Good.
had a question on the
Okay.
first slide on the question you asked about the red and blue balls.
Okay, go.
Okay.
Yeah, the answer didn't really make much sense to me. I mean, those two events happened in an order, so how can we conclude that the probability of the second event affects the probability of the first one?
I mean, it's a great, I really would like to even just this tutorial be about that. So I don't mind to spend time. Anyone or Rahel, like, can you try to answer that?
Can you also open the slides so that we can talk about that
Exactly.
while we see? Oh, all right, thanks.
So I want some discussion here. So anyone who wants to, who's clear and who can answer, or who thinks who can explain that, I would like them to try. So the Biniam's way, go on, okay, right here.
His question is not clear.
Biniam, can you repeat?
Yeah, so what you said was the probability of the second event being known affects the probability of the first one. If those two events are performed in an order, I mean, if we're concerned about time, how can we be sure that the second event affects the probability of the first one?
Yeah.
Okay. I think we are calculating probability, right? For example, if you say 0.5 probability, doesn't mean it means it's either. But probability might increase and decrease. It doesn't affect the real result, but it affects the probability. But in our case, if we have two outcomes, we're pretty sure that the second outcome can like 100% change the first outcome because we only have two outcomes. You get what I'm trying to say? I mean, if you get red at into the second time, it means the first was blue because we only have two, red and blue. But if we have like more more balls, not only two, but more balls, maybe the probability might be affected. It doesn't mean the outcome will change, but the probability we have, the thing is, the probability will change. It means, I don't know how to explain it, but
I think it's great, but it's like, let's see if that is not clear, someone else can make it clear, or if Biniam is clear, just let's go on. I think in my opinion that's a very strong argument as well, what Rahel gave. But let's see, anyone else can try to attempt in their own understanding.
Yeah, let's modify the question a little bit. So when we talk about the probability of an event, are we just merely talking about the randomness, I mean the nature of the event turning out the way we want it to be? Or are we just, I think the answer is in the statement you mentioned earlier. You said probability is logical, not timely. So like when we talk about probability, like does it mean we don't have to care about the order events happen?
Exactly, that's what it means. It's in a way assigning probability. I think as Rahel was suggesting, it is not the actual outcome, because probability, probability just means how likely an event was. But once you observe the event, of course, it's different. So, but it's really gone.
Of course, the order doesn't matter, because if you get blue the first time, you're fully confident that you get red the second time. And if you get red the second time, you're fully confident that you will get blue the first time. So the order doesn't matter. The logic is what matters here.
Yeah.
I think.
Excuse me, can I get one chance, please?
Yes, please go on. I mean, this is all gone.
Okay, thank you. So this is just for everyone. You're going to enjoy this problem. So I mean, to answer Biniam's question, it's just all about not the events. So we need to think more of it that the knowledge, the new knowledge that we gained helped us to, adjust our probability assigning, nothing more than that. I mean, the knowledge we gained about that the second ball was blue leaves us with 0 chance the first one was blue. It's just that the knowledge is what's making the difference here. But to just give you something interesting, read about the Monty Hall problem. It's in 1970. I believe everyone will enjoy it. It was there was a TV show, Deal or No Deal. So it's much more similar to this one. And
so Nahum, I have that later. So just instead of spoiling it, I will exactly that I will explain. But that is a very similar thing, which is if anyone doesn't know, I will have just that picture which explains this another basically brain teaser on that. So like we can continue. That's there.
Okay.
Yeah. So
hello, Yababel.
Yes.
Yeah, I wanted to add something on the question Biniam asked.
Okay.
Yeah. Because there is it's without replacement draw.
Yeah.
Will be different from the sample size of the second draw. And as such, the probabilities won't be the same. I don't know if this is okay.
So sorry, just because you were breaking, I didn't hear. So what? Say it again.
Yeah, I'm saying that because it's without replacement.
Yes.
The sample size for the first draw will be different from the sample size of the second draw. As such, the probabilities won't be the same.
Yes, but yes, that's a very good point. So definitely, yes. Go on. Who's that?
Can I talk?
Yeah. Who's yeah.
Okay. Yeah. So basically, I think this is if we are sure that the outcome of the second one is right, that means we are left with the previous one will not be what we are left. Before we did our first picking, we had about, I think, 5 red and 3 blues. So if the second one turns out to be a blue ball, that means our initial first pick will be like 8. That is like 5 red and 3 blues. It will actually affect because now we are left with two blue balls, and then we have 5 red balls. And the probability for the first one will now be like, let's say, first one will be 1/3, like I said before. And then if the second one is 1/2, because the second ball, if the second ball is red, that means we are left with 3 blues. And then the probability, I don't know if it's clear, I don't know.
I mean, I think that's correct. That's absolutely clear. But the one thing I want to say is, this is why didn't I give one red, one blue? It's to confuse you, right? But the best example, the equivalent example, is to just reduce the problem to a simpler. Instead of 5 and 7, make it 1, 1. And then it makes a lot more sense. It's so easy. It becomes 0 and 1, and then it kind of, you can understand it. So it's actually, you're right. I'm just saying it's much simpler. This is for a brain teaser, 5, 7, but it's an equivalent if it was 1, 1. 1 red, 1 blue.
Yeah, that's true.
Yeah, so that's the thing. But I think, yeah, just to close it on this one, yes, the probability will order, the sample size changes, but at the same time, the probability changed, and it didn't matter the order. As Rahel said, if you had known the first one, you wouldn't even do the second one because you know exactly automatically. But if you didn't know the first one, then by the time you know the second one, you know the first one. So the order doesn't matter, like which way you do it. So I hope that explains. And this is, again, just thing. And then I will just go because we are, hopefully it's clear for most people. If not, we'll continue it, okay, via Slack. Now the question is, what is probability? How do we assign probability?
That's about the, hello?
Yeah?
Yes, I don't seem to understand that induced and the other probability stuff. Go right. The induced and the other thinking pressure, something like that.
Sorry, I didn't hear because it was interrupted.
Really understand that induced and the other pressure probability stuff that you talk about. Induced or something.
Induction. So with
the ones you compare together. Huh? Yeah.
So the inductive reasoning versus the
deductive. Go over it, just like.
Yeah. So the inductive.
Yes.
Exactly. So it is about what ways you do. The first one is assumes there is a fair coin. So when you start from that kind of thing, or when you start from an axiom in mathematics, and then you do experiment, and then the outcome is told for you, then it's really purely, it's not probabilistic, because you know it's fair. That means you know it's probability. And then an experiment is carried out, and then, you know, basically you're just computing the probability, okay? So it's kind of, it's really, there is nothing to answer here in the deductive reasoning, because it's, you have to change, you know, basically, you know, the probability as well as, you know, you have now an experiment and nothing to do. In the inductive reasoning, that's a different one. You actually only get the data. So that means 7 heads out of 10 tosses. Okay, there was 10 coin throws, and then you got 7 heads. Now you want to answer a question called, is the coin fair? So that's a kind of inductive reasoning, because you don't know if the coin is fair or not. You start with something you don't know. The cause for the data is unknown, and you want to know what possible causes are there. So is that clear? So that's the differences. In one, it's mathematics. So the deductive reasoning is purely mathematical, because there is nothing to answer. Everything is completely specified. And so it's just, you start from something and you derive its kind of logical conclusions. And the second one, you get a data, you have no, you want to infer back what kind of thing it is. In this case, as I said, whether the coin is fair or not. But in another example, as I gave, let's say you have the data which tells you 10 years of rainfall, and then you want to ask, like, how likely is the drought in Cape Town next year, or like in Senegal, in Dakar next year. So it's kind of, you want to infer about drought. In this case, drought is the kind of the hypothesis you want to test, okay? So hopefully that is, or if you have a set of pixels, you want to ask how likely it is that it is a cat picture. That's another way. Hopefully that answers your question. Okay. So
yes, very
okay.
clear. Thank you.
So what is probability? Again, it's really the first, and then how do we assign probability? This is really the same as, like earlier I tried to allude, one cat, one house, one world, whatever. One part is just this, what is a cat? What is probability is like asking the same as like, what is a number? But that number has, its interpretation differs. So one house, so you can't ask what is one sometimes without saying, it kind of becomes harder, right? So it's kind of actually really is like a number, and then what the interpretation of that number is what really usually what we are asking. And assigning numbers like is kind of a philosophy, right? The way you assign, for example, the way you kind of rearrange your object-oriented code is really subjective. And the same, like it depends on that. And so what you call one house, a house, does it also represent a building? It's kind of like, so it kind of, this becomes there. And how do you assign probability is where I'm going faster, but this slide will be the kind of the key you have to understand. In one part, probability has syntax. So that means the things that you write, syntax is like P of X and Y given Y, all that thing. That is mathematics. That is the same. And it is not at all subjective. It's the most objective thing. It's like mathematics. It's like calculus. It's like anything else, okay? So the syntax part of it, it doesn't matter which interpretation you adopt, it works. It's like writing two, in number theory. Just like that, it's valid, and it's specified from the kind of mathematics called Kolmogorov axioms, and that's it. But the semantics, which is like the interpretation of it, has, of course, difference. How you assign probability is different, depending on which kind of philosophy you adopt. And the first one, like the two common ones, are frequentist. So that means you kind of assume, you assign probability based on a hypothetical frequency, like of how often something happens. And then another one, what we call Bayesian, it's not really, doesn't matter how often, whatever, you can't measure that. But what you do is that your belief, your degree of belief. So the very best example what I give is that if you start from a belief that God exists, that nothing, no evidence you need to change that. So that means it's the probability is 1. Like you assigned a probability 1 to God. So that means basically there is no theorem, there is no data. So that data should be in Bayesian way, a new data will come and then you will renew your belief. But in this case, if you really have a phase, you don't change it. That's why, like, however data you show to a believer, they won't change, right? Because that's why it's a Bayesian way. And the only way you can change a belief or a data can change you only if you didn't assign 1 in the first place. So, and if somebody assigned a probability of 0.9, that means they are likely to change, but you have to get a lot of data to change them. If someone assigns random probability, like half-half, then that person will be a lot more rational, and with the data, whatever it comes, will change them. So that's a kind of way, so that's what's a Bayesian way. Bayesian way, you change your belief. Probability is a kind of a degree of belief, and that you change that degree of belief based on data that you see, okay, or based on data that you get. So that is, and then I will talk about the first one, which is the syntax. The syntax, whatever you talk, whether frequency, whatever, it's fine. So Px usually means probability of x being a random variable. What you really, there's no probability without conditioning on something. So that means we always condition it whether we write it or not. Usually when we say Px, there is an inherent thing called I. That means information, background information. Okay, so that basically is just, and then there are only 4 rules in probability syntax, basically, whatever, probably it's called probability theory, that you will use. There is nothing else that you do other than using these 4 rules. Everything you have seen in probability, Bayesian or whatever, has been done through that. So using this operation, the sum rule, that means probability of X or Y is equal to probability of X plus probability of Y, and if they are correlated, probability of XY. You know, so you subtract that. That's the sum rule. The product rule, probability of X and Y happening, is probability of X given Y. So that's where conditionality comes, times probability of Y. And what is called a normalization rule, the normalization rule says probability of X and anything that is not X has to sum to 1. And the marginalization, which is another very important, is that if you have a probability distribution of P, X, Y, Z, blah, blah, and you want to only get just the probability of X, then you have to take the integral or the sum such that that's how you do. Like, for example, if there are 2 quantities in this case, then to get probability of X from these 2 distribution, you say probability of XY plus probability of, you have to sum everything that's not also Y. So that's the kind of this one. These are the 4 rules that you need to know, and you have to understand that you can read every single probability theorems, blah, blah, that is derived. They are derived from here. Everything about probability is there. Okay. I wish I'm going to go back to this one because this is a very important one, but probably I should, because even if we don't have time, I feel it's the most important. So here is another kind of brain teaser. That is, so let probability of X given some information is not 0. Let probability of Y given some other information that okay is not 0. So what examples satisfy this condition? So you have to, I'm just asking you to read this mathematical notation and to come up with an example. Okay. In another way, just before I forget, what that means in probability is why we need always to condition an information means whether you are a human or a machine or an alien or anything, probability assumes if you have the same background information or if they have the same information, you must assign the same probability. Otherwise, it becomes subjective. So that's why we need that information. And why do assignment change? Why do people sometimes assign for a probability of rain tomorrow different? That's because their information is different. So this is kind of like a sink. It takes all the thing that we don't know, kind of puts it. That's why all the problems about probability comes, because computing probability all about is like, how much do I know? Sometimes what if you forget? So another way I will ask you is that, guess my mom's birthday. Just anyone. Just anyone can write anything. The first one, who's going to write the first? Guess my mom's birthday. Okay, Biniam said July 16. And okay, no, I'm just going to take, I only need one. Okay, then I ask you, it's either July 16 or October 3. Do you change, Biniam? Okay, Biniam changed. Who else? Is there anyone who doesn't change? Okay, Mwakedi says no change. Why? That's really nice. Now we get into another debate. So can you unmute and kind of give us your reasoning? Even if your reasoning means like I feel it, that's fine.
Hello?
Hello, yeah?
I think I wouldn't change because maybe he's right.
Maybe he's right. Okay.
Yeah.
Okay. Can anyone come and try to defend that? So especially those who haven't spoken before.
Hello.
Hello. Yeah.
So now that it's been narrowed down to two outcomes, so it's either one of them. So the getting it correct is 50-50. So whether
Okay,
you
that's
change,
no. Just let's stop it. That's a very interesting one. Is it 50-50? Who thinks it's 50-50?
because it's two dates, one or the other, so it's 50-50.
Sure, but that's what we have been talking. Is it now 2 dates only? Is it just 50-50?
It's 50-50.
Go on, Ilakara, just so, but go on.
Okay, basically, it's 50-50 because it's an or statement. So it's either this or this. No one is sure. Even you are saying or, it might not be the October 16th and it might not be the July. So
I mean, I know you must assume that I know my mom's birthday.
Okay, well, I won't change because it's just like or it might be like
Okay,
me
great.
guys said it might be yes or no.
You make a point. Now I'm going to ask another person who's depending on the other one why they need to change, and Adnan or anyone. I think I have seen also some others before. Natnan, just can you, Adnan? Do you want to say?
I think I have something to say.
Hello.
Hello. Yes.
Yeah. Go on.
So this is my argument. Yes, on this case, I think what has maybe brought up this topic is does the party have a prior information on this particular case that you're trying to resolve? And I think when you asked about your mom's birthday, we made random choices because we had no information. But you have the information, and maybe you gave us what if we 3rd September? I think we'll have to change because now we are relying on you. You have the information we don't have. Yeah.
Great.
So it's not 50-50. Yeah.
Okay. So I wish that we can continue. I mean, time is limiting, but it's definitely not 50-50. It is because exactly what it's in the first one, each of the dates, the 365 dates has equal probability. By the second time I said it's either this or that, I basically said all the other dates 0. And by the time someone said 6th January, whatever Biniam said, that had still the probability, it didn't change. It just because the information, the second information I gave didn't change that, but annihilated all the others, like the 364 dates. It basically it splitted the data into 2, the one that you said versus the rest. But now I assigned 0 to all of them, and then the second point I say, which is 3 October, becomes now 360. Its probability is 364 over 365, almost 1. Your probability, the first probability you assigned, was still 1 over 365. So you must change. Like it is exactly the same thing as what we are gonna. If I were to show the 3 doors, Biniam is why. Oh. Yes, because why do you think it would change? The first point you say it like it is, when you take one sample, it's basically saying let's label that one red, and then let's label everything else blue. Whatever you didn't say, that's exactly what is this thing. The probability of all events except X. So now the probability was the probability of X plus the probability of, that's called the probability. So I'm just going to come here. So this was true, right? So the probability of the dates Biniam gave plus all the other dates that Biniam didn't give, that means the 364th days should be summed to 1. Now I am assigning like this thing, the X, still the probability is the same. Like he didn't, there's no information on that. I didn't say you are right or you're wrong. I only created another information which affects the distribution of the X bar, which is saying like, oh no, it's either what you say, which is still the same probability, but then I turned all the others into like 1 and annihilated all of them to assign to be 0, and then I assigned another date to have some probability. And now you have to choose. Given that this probability has to still sum 1, this one should be 1 minus this. So that's why it's kind of, this is just a normalization. Like basically whatever I said is just a normalization. So if you don't understand, we can continue, but that's the reasoning.
So it's 1 minus the probability
of the first one you said. So if the first one to get it right was 1 over 365, so 1 minus 1 over 365 basically becomes basically 1. So you should just change because the second one has a high probability. Okay.
Because both will always sum up to 1.
Exactly, and also because I know my mom's birthday. That's exactly the point. That's how I assigned the probability. Like I changed the probability assignment, me having the information, which is called in this case the prior, exactly earlier what BioDev said. I changed the information. The prior, I set the prior to be 1 for those 364 days. I set to probably to be 1 at the date that I know, and then I just basically cut out the other ones to be 0. So exactly. Okay.
So what if you don't know? Sorry, please. What if you don't
I mean,
know?
if I don't know, of course, then that's not probability. That's kind of nothing. It has to sum 1. It has to sum to 1. So otherwise, you know, then it doesn't work. The normalization rule, then it's not a probability theory, because then the normalization will not be satisfied.
Well, thank you.
Okay. So, yeah.
Hello. I don't understand why. I don't agree why when you limited the sample to 2, then you said
because it's not 50-50, because it's not like you forgot the first information you had. The information you had in the beginning, that is like that I know that you don't know, and you assumed, you chose one number randomly, which has a probability of 1 over 365. But now my probability comes and multiplies yours. My probability means selecting from those 364 other days that you didn't select. I set all of them to 0 except 1. And then now when that's what it's changing it. So the second date actually incorporates a prior information from me.
Okay, so is he required to make another selection again from those 2, or does
he has to, but now he
to
has to. I mean, it's basically now one. The probability of these 2 has to sum to 1, right? That's exactly what we are saying. The probability of these 2, in the first time, X had 365 possibilities, and it had to sum to 1. That's why the one date that you select was its probability 1 over 365. The second time, the probability you assigned didn't change, because I didn't change any probability in that. I didn't give any information on that. But the second, I said probability on the other one. Basically, just from the 364, I chose 1. That's kind of through my prior information, and they have to still to sum 1. So by just taking 1 minus the previous probability, you will know the probability of the second one. So it's not 50-50. The second one is different.
Okay.
Yeah, Bhavan?
Yes.
But what if I got the question right and her birthday was on 16th July and you just mentioned October 3 just to mess
No, I
with me?
wouldn't. I mean, in that case, so it's called model selection. So that's true. It could, by chance, you could have, but that's exactly what we are calling probability. It's just only chance calculation, and you should always choose the information with the higher probability, which doesn't necessarily mean it's not about right and wrong. It's about higher probability. But you're right, it could happen. But that's model selection. If you have guessed, if I have asked you 365 days, of course you could have, by one of them, in one of them you would be right to stick. But so let's imagine a betting. We are betting for each of this. We are betting $1. So, or whenever, one bird, whatever unit, and then, of course, if we play 365 days, you will win $1, but I will win $365. So do you want to be, always the probability is that saying, do you want to, in a longer term, do you want to win more, or do you want to once to be right? Yep. So hope that's clear. And I would just go Bayes' theorem, which tomorrow Jean would mention. We'll talk on that. There is nothing different about it. The most important thing is that it uses two of these properties. The first property is this, a product rule. But the product rule states that in the sum rule states that X or Y or X are the same, because probability is interchangeable, symmetric. Now, that means probability of X and Y is given probability of X, Y times, given Y times probability of Y. But it's the same, because given that probability of X, Y is the same as probability of Y and X, probability of X and Y and X are the same. So if you write it now with Y and X interchanged, you will get probability of Y given X times probability of X. That's it. That equality, this is exactly what I'm saying. Probability of X, Y, which is the same thing, you can write it either like that, or you can write it like that. But because the two are equal, if you rearrange them, you get this thing, what you call Bayes' theorem. So Bayes' theorem is nothing more than applying, using the product and sum rule, or the symmetry rule and the product rule, and basically you get that. That is all for what you know about Bayesian theory. This is the starting place. For everything you know, that's just applying these two tricks, and then you get a Bayes' theorem. And from then you continue your constructing all Bayesian theory that you ever have seen. And within that, we have named them, if you change variables, like this is what likelihood, prior, evidence, posterior, all that is just on that, it's a name. If one is data and the other one is parameter, then yeah, this is what is. And I think tomorrow you will come to it, so I'm not gonna just, I will probably continue this talk on, because I really like to continue on Bayesian versus frequencies, but also probability theory, events and outcomes. But for now, it's the last one. This is my brain teaser. So the first brain teaser part is that you have to, so given probability of X given some background information is not 0, probability of Y given background information is not 0. Now I ask you to read this thing and to give me an example that satisfies this condition. Anyone? First, who's, okay, let me break it into two. Who can read this one in kind of English? The equation.
Yeah, can I talk?
Yep, go on.
Okay, so basically, okay, so we are asked to let the probability of X given high, L, is not equal to 0, and the probability of Y given L is not equal to 0. What examples satisfy the following? Probability of X given Y products of L is greater than the probability of X given L or high, something like that.
So great, yeah. So how do we, that's great, that's correct. So, but who can go further, interpret it in kind of example, with an example?
Okay, sorry, let me say something.
No, let's give to other people who want to say,
Okay.
just so that I think it would be nice just if people kind of, if they understood it, just give one example to make it more interactive. It's a very simple thing. Is anyone saying? Hello, Adnan. Yeah.
Yeah. Okay, so it's saying let's probability of x given an information not equals to 0. That means that's saying that the event will happen or will not happen, because if it is equals to 0, that means it is impossible.
Yeah.
And that the probability of y given an event is not equals to 0, that means it may happen depending on the probability. What examples satisfy the following? Probability of x given y given an information that is probability of x will happen given that y has already happened is greater than the probability of x happening. So
Fantastic.
I think that's,
but what does it? Great. That's exactly what it is. Absolutely nice. Now the second question is that real life example that will satisfy this condition, this inequality condition. So give what x could be, give y what it could be, and that it will satisfy. And then there's even a very simpler thing, a generalized thing. But first, let's just get one simple example.
Can I try?
Yeah, go
on. Okay, let's say I denotes the probability of it being a summer. For example, let's say in Ethiopia.
Yeah.
And let's say X represents the chance of raining and Y represents the chance of the day being cloudy.
Okay.
So if the chance of raining in the summer is not 0 and the chance of being cloudy in the summer is not 0, then the chance of raining while it's cloudy in the summer is greater than the chance of raining in the summer. Does that make sense?
Yes, I mean, absolutely does make sense. And I mean, perfect. Thank you. And probably some people may, if they haven't understood, you can ask question or you can also give your own example based on this. But excellent. Yeah. And some people also, you can generalize. What does it mean from that example? For example, what do you notice? This is kind of a general, there is a generalization to it that applies to everything. So it's kind of think about what does it mean? What is, and you have done it already many times, million times probably. I mean, not million times, but a lot of times in the past 2 weeks, you have been computing something. So I give you a hint. You have been computing correlation.
Yes, I think I've got the hint.
Go on.
Okay. Yes, I'm saying. Yes, I'm saying. Maybe for this scenario, I think the probability of one event happening depends on another event. If I'm getting it right, that is.
Yeah, but like I think the summer thing, the summer example that Biniam gave is a very good hint. And then I give another hint for the generalization. But maybe let's do one more example, specific example to see the generalization. So you're kind of right, but it's like I want the generalization to emerge from you. But generalization usually happens if 2 or 3 specific examples come out and you see a pattern. So
okay, let me try something.
Your background is quite loud. I think you will tolerate probably, or
please apologize
my volume.
Very seriousness. So I'll say the probability of buying a company and probability of the company making money. Probability of X, let's say P of X is probability of me buying the company that we talk about, telco. Then Py is probability of me noticing that the company is making money. So I would say probability of me buying the company, if the company is making money, is greater than the probability of me buying the company. That's what I'm saying.
Very hard to hear for me. So, if anyone heard and there's a big environment, it's quite loud the background.
Yeah, I muted because the background is not hearable. There is too much
Yeah, it's
sound.
quite
Yeah.
loud. Yeah. So good. Okay, Janet, you want to say something? I saw Janet's mic was on, but probably not. Who else can give similar example as Biniam?
So I can try.
Go on.
So probability that you get a job, given that you finish the training program successful, is much greater than or equals to probability that you get a job.
Without a training. Great.
Yes, without
Fantastic. That's beautiful. Thanks. So maybe one more information. People are, aha.
Can I try?
Yes.
Okay, so assuming you have two kids and say X is a girl and Y is a boy, so the probability of the kid being a girl not equal to 0, and the probability of the kid being a boy not equal to 0. So the probability of the kid being a girl given Y is a boy is greater than the probability of a girl.
It kind of applies, yeah. Just given if you had the prior information that the person has two kids and they have different gender. So that information, earlier what Biniam said, information being the summer, in your case, that information, if exactly, it will work if that information is, if you specify that background information being that the person has two kids or two kids or multiple kids, but that one is a girl and the others are boys. And then exactly your algorithm, yeah, your analogy, your example will work.
Okay.
Great, thanks.
Okay,
but
sir.
is there anyone
Can I go again, sir?
Huh?
Can I go again? My noise
yes
is better now.
now your mic is much better. Earlier I was almost crying. It was too loud for my ear. No, it's okay.
I apologize for everything. And what I was saying is probability of binding telco is P of X. Then probability of telco making money, PY is probability of telco making money. So I say probability of X, probability of telco, if P of XY is probability of buying telco, if telco is making money is greater than probability of just buying telco. That's my illustration. Yes, sir.
Oh yeah, yeah, I think that, so now again, what is the background information you need for that to satisfy? So the probability of X is probability of tail, yeah, that I, in this case, the background information that you as a buyer knows that telco is making money.
Yes.
Okay.
That's the new information.
So yeah, but that's what I'm saying. There is no probability without specifying some background information, even if we sometimes don't have to state it. But it's very important to know if two people don't have that same background information, they can't assign the same probability. Great. So okay, so we are having a few examples. Who can just get the leap, the phase leap, or kind of like get like what is the pattern between all of them, and what is the generalization? Okay, I think we're way over time, so I'm gonna just say it. It's really saying, it's somehow is really saying this. If two things are correlated, then knowing one should give you information about the other one. Therefore, almost always this thing will satisfy if two are correlated. If the two are not correlated, X and Y are not correlated, then knowing Y doesn't really give you any information. Therefore, it will be equal sign. That's the only thing. So that's why if two variables are correlated, then definitely you gain information for knowing the other one to say about earlier, we said about blue and red ball, because they are correlated 1-1, you know, whatever number. Knowing one basically just gives you information. In this case, even all information you need, because they are 100% correlated. All information about the second row. You know, so it's basically saying if two variables are correlated, knowing something about the other one will give you information about the, you know, the one you're looking. So that's exactly that's why the summer, blah blah, cloud, exactly when he said cloud and rain, that's what they are correlated. So seeing the cloud, you know, is more likely kind of to give you the about rain information. If they are uncorrelated, of course it will be the equal sign. Okay, so that's how you read it, and that's why this is always satisfied. So with that, I hope you gain some. Huh?
Can you go over what you just said?
Sorry?
The last explanation, I didn't get it.
Yeah, so what I am saying is that this is about information. So correlation means that you know something about one thing, then you will know about the other one. If the correlation is high, that means you will know more. If it's 100% correlation, that means you will know a lot. So in this case, the red ball and the green ball, knowing there are only two balls, correlates, and they are red and blue, that basically correlate these two. That means if you see one, you get complete information about the other one. So because they are correlated, just any knowing about the second row basically tells you everything about the first row, or knowing anything about the first row tells you everything about the second row. If the correlation is smaller.
Thank you.
Great. Okay, awesome. So I hope that you got now a way how all these kind of, you know, in the mathematics, whatever, just probability of X, Y, blah, blah, when you see it, it's just simply in English, but somehow in variable form. And also that, you know, you kind of got an understanding about inductive reasoning, hopefully. So with that, we will close this one. Any question you have, and this will help you. I think all the others that you this week, what you're going to do about probability distributions, blah, blah, kind of makes sense. It's the probability distribution is basically assigning probability for each value. So for example, if you have a Gaussian, it says like, okay, within that interval, what is my degree of belief? If it's Bayesian, it's like, can I believe, let's say a coin, you know, the probability distribution of a coin, head and tail. So then you say like, oh, if it's a fair coin, of course, at 0.5, I assign more. And then I will assign less and less to 0 and 1. If it's not, you know, fair coin, then I will assign my degree of belief. If it's, for example, if I say that this coin has both head, then if I believe that, if I sense that that is more my belief, then I will assign more and more probability, high probability to 1, where it just says head, always that the outcome will be 1, I will assign high probability. And so you will get some kind of like exponential distribution. So all these distributions, blah, blah, comes also from this kind of assigning degree of beliefs. And then that degree of belief then kind of changes based on kind of information you get. So that's called inference, or, you know, so that's why I hope you got something out of it. And any question, what, you know, from this and others, we can discuss on Slack. Thanks, guys. And Sebastian, you can stop the record.
All right.
Great, guys. Cheers.